That's dramatic. Good evening, everybody. Thank you so much for coming out tonight. I got to have a tour of the library earlier today, and there are some historical books here that are atlases of the sky. Stars and their positions and their brightnesses over hundreds of years. And I'm so excited that I get to be part of building the atlas of exoplanets. And I'm hoping that in hundreds of years' time, they'll look in the Internet Wayback Machine at the Exoplanet archive as it is today and be like, oh, frames. So thank you again for being here. So as Eric kindly introduced me, my name is Eric. My name's not Eric. My name is Jessie Christiansen. I'm the lead scientist of the NASA Exoplanet Archive at the NASA Exoplanet Science Institute. My job is to keep track of all of the exoplanets we found and what we know about them. So let's talk about that. Okay, let's start off with what is an exoplanet. This is a not-to-scale graphic of our solar system. Our solar system, the census is 1 star, 8 planets. I know. We can have a separate conversation about Pluto afterwards. I'm really sorry. I'm not personally responsible, and that's all I can say. Our solar system has 8 planets. We have dwarf planets. This is the new bucket that we invented. Pluto got its whole own new bucket, guys. It's okay. Pluto still exists. It got to be the archetype of a whole new type of object called dwarf planets. So these are smaller planets out past Neptune in the Kuiper Belt. The reason we had to make this new bucket is we started to find more and more of them, and they didn't look like the 8 planets. They looked like a new type of thing. Scientists really like to classify things, so dwarf planets. We also have minor planets. That's everything else in the solar system bigger than a grain of dust that we've been able to catalog. There's over 1 million things that we found out there. Space is really big and really empty, and there's a lot of stuff in it. So, minor planets. But what are exoplanets? Exoplanet is short for extrasolar planet. These are planets outside our solar system. Typically, so far, they've been found orbiting other stars. So let's talk about that journey. Okay, as Eric mentioned, we've been thinking about this idea for a really long time. 2,500 years ago, the Greek philosophers were thinking about whether or not Earth was unique or whether there were many Earths. And they were doing this in a very hypothetical way. They didn't have telescopes yet. It was all a thought experiment. And they were thinking about Earth. Plato and Aristotle actually argued that Earth was unique, that there were no other Earths, that this Earth was the Earth and there were no other Earths. But the seed was planted. What if there were other planets? What would they look like? How would we find them? So let's jump forward like 2,000 years to the Renaissance, an amazing time for literature and art and science in the Western world. This is a quote from the Italian mathematician Giordano Bruno, and it says, "There are countless suns and countless Earths all rotating around their suns in exactly the same way as the 7 planets of our system." I'll leave it as an exercise to the reader which 7 planets he's referring to at the time. But this idea of the multiplicity of Earths, he was burned at the stake. I mean, he also said a bunch of really stupid stuff about the Catholic Church in Italy at a time when it was a bad idea to say a bunch of stupid stuff about the Catholic Church. But if you read the reason that he was burned at the stake, part of it was because of this heresy. This was heresy to say that there were other planets out there. He was a heretic for saying this. Luckily, these days, they don't burn people at the stake for finding exoplanets. Okay, let's jump forward to the 20th century. 1952. Otto Struve, who's an astronomer, he's thinking about this idea of exoplanets, as many people had. And he writes this paper. It's wild, you guys. This paper is like 2 pages long, and it changes the world. In this paper, he proposes 2 different techniques for finding planets, super casually, just off the top of his head. He's like, well, if there were planets orbiting stars, the stars would be dragged back and forward by that planet's gravity, the same way binary stars, 2 stars go around each other. If we could measure the velocity, we could see the planets. And if they were there, they'd also block some of the light. So if they were lined up just right, the planets would also transit. It's 2 pages long. And it changes the world, guys. Because 40 years later, using that first technique that he suggested, we find the first planet orbiting another star like the Sun, 1995, 51 Peg B. This won the Nobel Prize in 2019, finding this planet. Because this guy 40 years ago was like, huh, maybe. Because at that time, in 1952, there were no spectrographs that could do this. So he's just like, in the future, if our instruments could get better, we could do this. And I want you to hold that thought, because we're going to come back to it. Since then, okay, 1995, terrifyingly, it's like 30 years ago now. Since then, this is what's happened. This is a graphic, a video, showing the planets that have been discovered over the last 30 years. They're going to appear in the sky where we find them. The tone of the note tells you how close that planet is to its star. A very close planet makes a high note. A very far away planet makes a low note. So I'll let you watch for a moment. And you can see, as time goes on, it fills in and fills in and fills in. We're up to 2009 now. This is when Kepler launches, and it's about to explode. We're going to talk more about Kepler. This is the Kepler field here. This is the patch of sky that Kepler looked at. Thousands of planets got announced in one paper. This is the ecliptic plane. This was another survey that was done by the Kepler telescope, and you can see many more planets appearing. And then in 2022, we hit 5,000 planets around other stars. So in 30 years, we went from just this idea, and I would say it wasn't even an idea, I would say it was a hope, right? We wanted there to be other planets. We wanted not to be the only solar system. We went from a hope to 5,000 planets around other stars. And I'd say that's pretty cool. It's pretty cool. So let's talk about the planets that we found. There's only 2 plots in this talk. You can do this, I promise. This is the stage ends there. This is a distribution of planets we knew before Kepler launched. This axis here is how far away the planet is from its star. That way means further away. It's in days, so out here at 365 days is the Earth. This axis, I'm going to look now before I walk, this axis is how big the planet is relative to Earth. So Earth is 1 Earth radius. So this is the Earth. Welcome. This is the solar system, Mercury, Venus, Earth, and Mars. These were all the planets we knew before Kepler launched. And one thing you should hopefully take away pretty much straight away is they didn't look anything like our solar system planets. They were all bigger and they were all closer in. You see this cluster of planets up here. These are all Jupiter-sized and above. This is what it looks like today after Kepler and after NASA's other very successful missions. This space has really filled in, and we're going to talk about this pink square here. The search for Earth 2.0. So whenever I talk to people about finding planets, we are human, and we have human feelings and human thoughts. We want to know if there's another Earth-like planet out there. We want to know if there's another home, another place where life could be. A lot of people's energy and time has gone into this question. The search for Earth 2.0. Does it exist and where is it? And so that's what happened, was the search for Earth 2.0. In 2009, we launched the NASA Kepler mission. Kepler's goal was to determine one number, one frequency. How common do planets like the Earth occur? Are they very rare? Is Earth the only one? Or are they wildly common throughout the galaxy? Does every star have an Earth-like planet around it? So Kepler had one goal, which was to measure this number. It's a 1-meter telescope that was launched in 2009. It spent 4 years looking at this one patch of sky that you guys just saw fill in on that animation. It's a little field in the constellation Cygnus, the Swan, which you guys can see overhead in the summer. And it looked at 200,000 stars in that patch of sky. The way Kepler works is using the transit method. So I remember Otto Struve's paper. There's like a paragraph in this paper where he's like, yeah, and if they went in front of the planets, they'd block some of the light. We could see that. This is how it works. So this is an animation of a system called TRAPPIST-1. TRAPPIST-1 is now one of the most famous exoplanet systems. It's got a very, very small, cool red star in the center of the system. It's about as small as a star could be and respectably call itself a star. Any smaller and it wouldn't be able to fuse hydrogen in the middle. And it has 7 rocky planets around it. Now, if you take that system and line it up just right, those planets pass in front of the star. So what we do, we make just about the simplest and oldest astronomical measurement. We just measure the brightness of the star with time. Just measure this brightness of the star over and over again. And what we see are these dips. Every time a planet goes in front of the star, it blocks some of the light. Now, it's a very simple measurement, but you can learn so much. The distance between the dips, these 2 dips of planet B, for instance, that tells you how long it takes the planet to go around. So Earth takes 365 days to go around. That's a year. So if you were an alien civilization looking at our solar system and you were lined up just right, every 365 days you'd see the Earth go in front of the sun. The depth of the dip tells you how big the planet is. A bigger planet blocks more light, and you get deeper dips, and a smaller planet blocks less light. So just with the brightness of the star, you've got how big is the planet and how far away is it. If you know the star, now you know how hot it is. If you know things about the equation of state, the size tells you whether or not it's a gas giant or a rocky planet. So you've got a lot of information. So this is what Kepler came up with. So this is the picture after Kepler. Now, Kepler's job was to measure how common Earth-like planets are. Did we find any Earth-like planets? No. There's no points here. There's still only the solar system. We still do not have any genuine rocky planets in the habitable zone of a star like the sun. Okay, so now we're getting into dangerous territory. And I'm not just saying because I'm walking to the edge of the stage. When scientists have data like this, which is complete in one area and incomplete in another area, we extrapolate. It's not always a good idea, but heck yeah, we're doing it every time. So we're going to take these planets and say, okay, we see the pattern, and we're going to extrapolate to here. So if you extrapolate, with all of the caveats that come along with extrapolating, we think that Earth-like planets are probably common. Somewhere between 10% and 50% of stars like the sun probably have a rocky planet in the habitable zone. So I'm going to let you sit with that for a minute. That's pretty big. 10% to 50%, up to half of stars like the sun, and there's, let's say, 10 billion of those in the galaxy, have a planet like Earth around it. That's 5 billion potential Earth-like planets. But I want to say again, we haven't actually found any. This is extrapolating, all extrapolating, and all of the problems that come with that. Okay, so what have we found? I don't want to say we didn't find anything. This is Kepler 452b, an animation of Kepler 452b. We see the data that I showed on the previous animation, not this. Okay, so this was one of the planets discovered by Kepler. That is a star like the sun that is orbiting, a G star. And it is orbiting with a period of about 372 days, which is pretty close to 365, so that's good. It's a little big. It's about 1.5 to 1.6 times the size of the Earth. And we start to get a little worried then that it might start to have a very deep atmosphere, which would mean that you couldn't have liquid water on the surface. So that's a little iffy. But the main problem with Kepler 452b is that it might not be there. When I say the period is 372 days, the period of the Kepler spacecraft around the sun is 372 days. So if you've ever worked with instruments, if 2 numbers line up in your data, it's not a coincidence. The fact that the Kepler orbit is 372 days and we found this planet at 372 days is not a good sign for Kepler 452b. It's a very, very low signal-to-noise detection. It's very hard to see. So it might be there, but it might just be noise in the data. There's a lot of other stars that have exactly this kind of noise. So it probably has like a 50-50 chance of being real. And if it's real, it probably has a 50-50 chance of being a rocky planet versus something like a small ice giant. This is as close as we got. But still, hey, Kepler 452b. It's got a 25% chance of being a planet like the Earth. Now, what Kepler did find a lot of, and what other missions have also found a lot of in the meantime, are rocky planets in the habitable zones of a different kind of star. So remember I mentioned TRAPPIST-1 is a cool red star, much smaller than the Sun, much cooler than the Sun. We have actually found tons of rocky planets in the habitable zones of these M dwarfs. And that's partly because of those two things I showed you about transit data. The habitable zone of an M dwarf, the distance you have to be away in order to be habitable and have liquid water on the surface, is much closer because the star is much cooler. So you don't have to be 365 days away. You can be 30 days away and still be the right temperature. So those dips that you're looking for happen much more frequently, which means they're easier to see. The other property is the depth. A planet like the Earth blocks a larger fraction of the light from a smaller star than a bigger star, just because it's the ratio of the sizes of the two. It's a circle in front of a circle. If you make the background circle very small, then the front circle blocks more light. So they're much easier to find, and we actually found a bunch. This is actually a graphic of Proxima Centauri b. Proxima Centauri is the closest star to us besides the Sun. When you leave our solar system and go out, the first star you get to is Proxima Centauri. It's a red star, it's an M dwarf. And it's also got two other stars, Alpha Centauri A and B. Those are those distant stars. They're a little bit further away. The closest star to us has a rocky planet in the habitable zone. Isn't that wild? Our very next door neighbor, the one we would borrow a cup of sugar off if they had it, has a rocky planet in the habitable zone. That's so exciting. But let me tell you why it's not exciting. We don't know whether rocky planets in the habitable zone of M dwarfs are habitable. The problem with being so close to the star is that stars are a really violent, energetic, not nice place to be, right? Like we wouldn't want to go to the surface of our sun. It would be bad news bears. And if you think about Mercury in our solar system, which is much closer to the star than us, kind of bad news bears. So if you take a rocky planet and put it right next to an M dwarf, we don't know whether it can keep its atmosphere. That's the key question right now. Can a rocky planet in the habitable zone of an M dwarf keep its atmosphere? We don't know. If it can, then they might be habitable. If it can't, then the surface is just exposed to the vacuum of space, and any water that's on the surface will just evaporate. There's no atmosphere to keep the water on the surface. That's the big question. This is how many rocky planets we found in the habitable zones of M dwarfs. Are any of them Earth-like? Probably not. We don't know. We need more information. So in the search for Earth 2.0, there's really only 0 so far that are truly Earth-like planets in the habitable zones of stars that we believe could have habitable zones. That's a bummer. Okay, so this question of whether or not these planets could have atmospheres will be answered by NASA's next big flagship mission that launched a couple of years ago, the James Webb Space Telescope. This is an animation of it unfolding in space. I'm apologizing to the astronomers in the audience because this is terrifying. They used to show us this animation before JWST launched, and every time you saw all these moving parts in space where if anything didn't go right, it was not going to work. It was just like, oh my God. It's going to work, it's going to work, it's going to be okay. So it's a really scary video. But what JWST can do is look at the planets in the habitable zones of M dwarfs and tell us whether they have atmospheres. So TRAPPIST-1, that small cool red star that has 7 rocky planets, so far JWST has looked at the first one, no atmosphere. The second one, no atmosphere. Now we're looking at the third one. The third one is the first one that's in the habitable zone. It's the first one that's far enough away. This is really, a lot of people are really paying a lot of attention to this. Because if this planet has an atmosphere, that changes the habitable real estate of the galaxy by 2 orders of magnitude. There's 100 times more habitable real estate if these planets have atmospheres, because they're so abundant and we see them everywhere, unlike Earth-like planets, which we haven't seen yet, but we hope are abundant. Okay, so 0 Earth-like planets in the habitable zones of Sun-like stars. I promise the talk gets better. It's not all bad news. What we did find was an incredible array of planets that look nothing like the planets of our solar system. Until 30 years ago, people who studied how planets formed and how planetary systems evolved had one data point, which was the solar system. If your theory didn't produce the solar system, then you threw it in the bin because it couldn't work. Now, there are so many types of solar systems, you guys. Okay, so back to this plot, which you're now all really familiar with. These are further away planets. These are bigger planets. So let's go back to this cluster that I talked about earlier. These are gas giants. They're Jupiter-sized and above that orbit their star in 2 or 3 days, a few days. We call these hot Jupiters because astronomers shouldn't be allowed to name anything. But they're Jupiter-sized planets that are really hot. And so this is a video of an animation of one called HD 189733b. I'm sorry, I don't get to name them. They all have garbage names. But this is a planet we've been able to study in a lot of detail because it's actually orbiting a star that's pretty nearby. It is so close to its star that when its star burps, when you would see a coronal mass ejection or a flare, it actually strips some of the atmosphere of the planet away. You actually see this cloud of material coming off the planet. And we've been able to study its atmosphere in so much detail. We've been able to measure the wind speed and the temperature, and that it has silicates in it. What happens when you take silicates and you heat them up a lot? It's raining liquid glass sideways on this planet at the terminator, at the edges of the atmosphere. It is so hot that it is raining liquid glass sideways. So hellscape, pretty bonkers, but interesting. Just wouldn't want to go there on vacation. Okay, hot Jupiters, giant planets heated up to thousands of degrees. We also have, if you see down here in this corner, these are rocky planets the size of the Earth that orbit their star in less than a day. This is 1 day. So these planets are going around their star in a matter of hours. Now what happens if you take a rock and you heat it up a lot to thousands of degrees? You get magma, you get melted rock. So this is an animation of a planet called Kepler 10, Kepler 10b. It was a tiny rocky planet that was found orbiting a sun-like star. It orbits in just a matter of hours, so it's tidally locked. So our moon is tidally locked to us. We always see the same face of the moon. We never see the backside of the moon. This planet is tidally locked to its star. It's so close that it always shows the same side to the star. The substellar point, the part of the planet that's facing directly to the star, is thousands of degrees. So we think it's just a magma blob floating through space. So we call them lava worlds because we shouldn't be allowed to name things. But this is, if anybody gets car sick or vertigo, just close your eyes for like 20 seconds. And I'll tell you when it comes back. This is an imaginary fly-through that NASA made for this first rocky planet that Kepler found. This is all artist's imagination. None of this is real. All we know is it's rocky and it's hot. So we believe that some of it is magma. And you see these cool ocean worlds. We're going to do like a wild flip at some point that I feel like they added unnecessarily. But now you can see the sun. Now we're going to flip, so close your eyes if you get sick on roller coasters. See, right? So this is the lava world. This is another brand new type of planet that we don't have in our solar system. We also did find a lot more rocky planets further out than this, not as far out as Earth. So these are just warm rocks. We found a lot of Neptune and Uranus-sized things, so ocean worlds and ice giants. But what we found that surprised us was that most of the planets that Kepler found were in between, this big lump here, in between rocky planets and ice giants. So why was that a surprise? In our solar system, these are the 4 giant planets. These are the relative sizes to each other: Jupiter, Saturn, Uranus, and Neptune. And then in our solar system, there's a big gap to Earth. There's nothing in between the size of Neptune and Earth. And then you have Venus and Mars and Mercury. So there's really 3 size regimes in our solar system, right? You've got the rocky planets, the ice giants, and the gas giants. What we found was that the most common kind of planet was in between, not one of these size regimes that we had. And we have 8 planets. We're sampling a lot of the size regime. So we call them super Earths or sub-Neptunes, depending on where your funding comes from. If you really want them to be super Earths, that's fine. But the most common kind of planet is one we don't have in our solar system, a super Earth or a sub-Neptune. And we found a ton of them. Other sorts of things we found, you may recognize this scene. I'm sure there are sci-fi fans in the audience. This was from the 70s. Planets had not been discovered around other stars yet. This is Tatooine, right? This is Luke Skywalker's homeworld. And this is the double sunset. This was iconic and beautiful and such a fantastical science fiction idea. It's real. There are planets that orbit 2 stars. We call them circumbinary stars. This is a circumbinary star that has 3 planets around it. And I particularly like this one because this was before planets were found. George Lucas got the colors right. Right? He even got the colors of the stars right. He didn't get the sizes right, but again, 20 years before we'd found them. So we have found planets orbiting binary stars. This is really interesting because in fact, the majority of stars are in multiple star systems. So if multiple star systems can have planets, again, that changes the real estate in the galaxy for planets. Okay. We've also found planets orbiting white dwarfs. What's a white dwarf? You might have heard that in 5 billion years, our sun will expand and come out to about the orbit of Earth. That's its red giant phase. At the end of its red giant phase, it's going to puff off its outer atmosphere. Hopefully, will become a beautiful planetary nebula for some other extraterrestrial astronomers to admire. But what will be left in the middle is a little cooling chunk of carbon and oxygen called a white dwarf, which will just slowly irradiate out its energy until the heat death of the universe. That's what will be left. And for a long time, we didn't know whether planetary systems could survive this whole evolution, right? Like going through a red giant phase, becoming a white dwarf. Now, we've found planets around white dwarfs, so we know it's possible for planets to survive and persist around white dwarfs. So this is pretty exciting because it tells us something about our future. When our sun becomes a white dwarf, it might be possible for some of our planets to survive. What does that mean for the future of human civilization? I'm not going to be here in 5 billion years, but I'm hoping it means good things. We found planets around white dwarfs. Okay, so let's go back to TRAPPIST-1, which was this really cool system we found. What I didn't mention before, these 7 rocky planets are all closer to their sun than Mercury is to our sun. This is 7 planets inside the orbit of Mercury. These systems that we found are really packed. They're really crowded. And one of the ways they can be really crowded is because they're in resonance with each other. What that means is that the orbital periods of the planets are like clockwork. They're in sync with each other. We see resonances in our solar system. So the Galilean moons, if anybody, I know there's amateur astronomers in the audience. If you've looked at the Galilean moons, 3 of them are in a 1 to 2 to 4 resonance. So for every 4 times Io goes around, the next one goes around twice. And for every 2 times that one goes around, the next one goes around once. And the thing about resonances is they're very stable and they're very resistant to changes. So if you can get a planetary system in a resonance, then it'll lock and it'll stay like that for a long time. This is a really beautiful animation that Matt Russo made of a system that was found by citizen scientists using Kepler data, and the planetary system is called K2138. I'll start the movie. Now this is a system that's in resonance, 5 planets in resonance. And what Matt did was similar to the previous movie. He set the planetary periods to tones. So the shortest period planet has the highest pitch, and the longest period planet has the lowest pitch. The reason it sounds pretty is because they're in resonance. All the planets are in a 3 to 2 resonance with each other, which if you know musical theory, is the perfect 5th interval. These planets are playing Twinkle Twinkle Little Star. They're all in a perfect 5th interval from each other. This is your moment of Zen in the middle of the talk. And if you're interested in becoming a citizen scientist and helping us find planets like these, there's still an ongoing project called planethunters.org where you can go home tonight and use your computer to help us find planets. Unfortunately, Kepler had hardware failures. It wasn't able to keep observing. In 2018, it finally got turned off. And in 2018, the NASA Tess mission launched. Tess didn't have the same statistical question as Kepler. Tess is designed to find all of the closest nearby systems. And it's predicted to find something like 12,000 planets. So we're still at about 5,000. We're at about 5,500 at the moment. So this would nearly triple the known planets if Tess finds 12,000 planets. So that's the next thing. That's the thing that we're currently working on is Tess. The thing after Tess, this is the next thing that's going to get us closer to Earth 2.0. Probably won't get us there, but it'll get us closer. This is the Nancy Grace Roman Space Telescope, or an animation thereof. They also chose to go very Star Wars with this, very Star Destroyer coming in. This is a telescope that's going to launch in a few years' time, and it's going to do a survey for exoplanets. So I showed you in that plot that Kepler was sensitive out to nearly Earth, but not quite Earth. Roman is sensitive to the planets out here, further past what we call the snow line, where it becomes too cold. And we're hoping that between those two missions, we'll be able to work out this answer of how common Earth-like planets are. We'll get the further out data from Roman, we'll have the closer in data from Kepler, and we will extrapolate. And it'll be great. And we'll know how common Earth-like planets are around sun-like stars. Pretty sure. 5-10 years. We're real close. So this is just showing that this is the Kepler data, this is where we think Roman will be sensitive, and here is Earth. So we might find Earth-like planets, and we'll hopefully be able to nail down how common they are. Roman is expected to find 100,000 planets, so I have good job security for the next decade as the person who collects all of the planets for NASA, which I appreciate. And if you extrapolate the current rate at which we've been finding planets, we're on track to find millions of planets in the next few decades, which is very exciting. If you stop and think for a minute about what we knew about our galaxy 30 years ago versus what we'll know in 30 years' time, it's just so much more populated and with such a variety of myriad planets and myriad systems that it's truly an exciting time to be in the field. Okay, this is an image, or movie rather, of a planetary system called HR 8799. These are 4 giant planets, 1, 2, 3, 4, that we've been able to image over a 10-year period and see orbiting their star. Now they're very young, so they're hot, and they're very big. They're all bigger than Jupiter. So we can't use this technique, direct imaging, to find Earth-like planets just yet. So we're kind of back where the Greek philosophers were 2,000 years ago. We're thinking about Earth. We think that there are Earths out there. We're not sure, but we don't quite have the technology to do it. Right now, 2023, we don't have the technology to find an Earth-like planet in the habitable zone of a sun-like star. We can't do this. So we're kind of stuck again. But this time, we have a plan. This is NASA's roadmap for exoplanet missions. So tonight you've heard about Kepler, you've heard about Tess, you've heard about JWST, you've heard about Roman. So let's talk about NASA's next big flagship to look for Earth 2.0. It's called the Habitable Worlds Observatory. Every 10 years, the entire astronomy community in North America gets together and talks about what they want their priorities to be for the next 10 years. It's really valuable for funding agencies like NASA and NSF if all of the astronomers have gotten together and really been like, no, it's the search for Earth 2.0 that's the most important. That's where we want you to put your money. And in fact, the 2020 Decadal Survey, that is what popped out as top of the list, inspired by the vision of searching for signatures of life on planets outside of the solar system and by the transformative capabilities such a telescope would have for a wide range of astrophysics. The survey, the Decadal Survey, recommends that the first mission to enter this program, which is described here, is a large 6-meter aperture infrared optical ultraviolet telescope. That is what is now called Habitable Worlds Observatory. I was lucky enough to be chosen to be one of the 20 scientists on NASA's committee to start defining this telescope. It's very, very cool. We have our first face-to-face meeting in 2 weeks where I get to meet with the 19 other scientists and we get to start defining this telescope that will find Earth 2.0. It's going to be incredible. So let's talk about what it'll do. This is the current capability. These are giant planets very far away from their star. This is the scale here. 1 AU is how far away the Earth is from the sun. So the Earth is in here, in this image, if there was an Earth-like planet orbiting this star. So we're not there yet. This is a simulation of what our planetary system would look like if you could observe it with Habitable Worlds Observatory. You can see, we can just get to Venus. You can't get inside of that. You can see Earth, and Jupiter's a giant, booming, lovely big signal. So the idea is that we will search 100 nearby sun-like stars and look for planets in their habitable zones. Now remember earlier I was saying we don't know how common Earth-like planets are. It's somewhere between 10 and 50%, fairly safely. So if we look at 100 planets, that means we will find something between 10 and 50 Earth-like planets, truly Earth-like planets around these stars. And importantly, what direct imaging gets you, this little blob of light, we can take that and put that in a spectrograph and spread that light out and look for biosignatures. So this is the holy grail of exoplanet searches, biosignatures. Sure, you found a rocky planet. Does it have life on it? That's the next thing. So here's an example. This is the other plot. It's okay. It's fine. This is an example showing what a spectrum of Earth's atmosphere has looked like over the last few billion years. So this is modern Earth, going back in time, going back to ancient Earth. You can actually see it changed quite a bit in that time. And that's why we need to have a model of what Earth looked like over Earth's whole history. Because when we find Earth 2.0, we don't know whether it's before life evolves, while it has simple life, after it's got complicated life, after complicated life blew itself up in a nuclear war. We don't know what it's going to look like. But Habitable Worlds Observatory will give us these spectra of these planets and finally let us actually look for biosignatures around a truly Earth-like planet. So Habitable Worlds Observatory is NASA's next big effort in the search for 2.0. And I'm very excited that I get to be part of the team from the ground up. So tonight we talked about the search for Earth 2.0. It's been going for a while. It's been going for 2,500 years. And we've tried. The Kepler mission tried, direct imaging missions have tried, radio velocity has tried, but we're just not quite there yet. So it's the search for Earth 2.0 in 20 years, because that's probably the timescale we're looking at for developing something like Habitable Worlds Observatory. And that might sound like a really long time, but if you think about the James Webb Space Telescope, which just got launched 2 years ago, that was in development for a really long time. That was recommended by the 1990 Decadal Survey and then launched in 2018. And Roman, which is launching in a few years, was recommended by the 2010 Decadal Survey. So that one is at least only 25 years. So these things take a while, and it's a big effort. And NASA hasn't done a good job with its budgets the whole time, right? You've probably heard that NASA hasn't done a good job with its budgets the whole time. But this is it. This is humanity's next throw of the dice to find Earth 2.0, is Habitable Worlds Observatory. So the next 20 years is going to be building consensus and building excitement and building motivational and building congressional support for Habitable Worlds Observatory. So I hope that you guys are as excited by it as I am and excited by the search for Earth 2.0. And in 20 years, I hope I'm back here at the Linda Hall Library telling you guys about the first Earth-like planet we found. Thank you so much.
All right, we have time for a few questions. I'll come by with a microphone. Just raise your hand. Yes, sir. You've always got a question.
So you've talked about a lot of upcoming projects. What I didn't hear you talk about was the new telescope being built in Chile.
Oh, the large ground-based telescopes?
Yes.
Yes.
And that's being billed as a planet finder.
Yes, so the large ground-based telescopes, there's 3 that are either under construction or being planned for construction. There's the European Extremely Large Telescope, which is nearly 40 meters. There's the 30-meter telescope. I'll let you guess how big that one is. And there's the Giant Magellan Telescope, which is about 20 meters. So these are all large telescopes that will be built on the ground. Now, they will do a lot of good work on exoplanets in terms of finding and characterizing. But the problem with being on the ground is the atmosphere. So there's clouds, there's water vapor, there's pressure cells, there's occasionally hurricanes. You know, being on the ground makes it very difficult to find tiny things in space, just because the atmosphere gets in your way. So they'll do a lot of good work, but part of the reason I didn't talk about them tonight is because I tried to focus this on Earth 2.0, and the large ground-based telescopes aren't hunting for Earth 2.0. They're hunting for bigger planets, closer in planets, exciting, interesting planets, and they'll do a lot, but not Earth 2.0. They just won't have the capability.
All right, we have a question here midway back in the room.
Yeah, so you said that the Kepler telescope was looking for planets closer into their stars, and then the Roman one was looking for planets really far away, and so you'd have to extrapolate to find planets closer to Earth's orbit. Why don't we just build a telescope that would look for planets in that range of their star?
Can you come to DC with me in 2 weeks and say to NASA, why don't we just build? So, the idea was, so Kepler, the part of the reason it didn't quite get to the sensitivity we were hoping it would get to is that stars are noisier than we thought. We'd never looked at stars at this precision for this long before. And we decided, before we launched Kepler, that our sun must be normal. It must be average. Most other stars like the sun should be the same amount of noisy as our sun is. And it turns out that was a bad assumption. Sometimes if you don't have the data to go on, extrapolation is bad. And stars are actually usually noisier than the sun. The sun is quiet. That's interesting, right? Like, what does it mean for us that the sun is quiet? Is it important? We don't know. We have a sample size of 1. So what we did was go back to NASA and say, hey, turns out we don't quite have the sensitivity in this original 4-year mission to get to Earth-like planets because of this noise. If you gave us 3.5 more years, we would just get there. We would be able to recover this sensitivity and find Earth-like planets. And NASA was like, that's great. Here you go, have some money, go do it. And then the spacecraft immediately broke. 3 months into the extended mission, the second reaction wheel broke, and we weren't able to point at that original field anymore. So then the question is, can NASA give us $600 million more to build another Kepler and launch it? And the answer is no. But there is actually a Chinese mission called Earth 2.0, which is going to be like Kepler Redux. They're going to send a big telescope to space and look at the Kepler field. I'm really hoping they share all that data and we get to find them and incorporate them with our data. But yes, why don't we just build a telescope that could do it? I agree. We will.
All right, I forgot to mention this. If you're watching online, type your questions in and we'll get to as many as possible. So let's take an online question right now from Jennifer, who asked, are there other targets looking for atmospheres around M-star orbiting planets other than the TRAPPIST system that James Webb could observe?
Yes, so that's a great question, Jennifer. I talked about TRAPPIST-1 a lot because it's the canonical archetype and there's so many rocky planets. There are other small M stars with planets. I remember I mentioned there's like 12. So we are studying those as well. At the moment, it's kind of interesting and kind of frustrating. Because stars are noisy and because planets are small, the trouble we're hitting at the moment is that the star is changing while we're trying to observe the planet go in front. And that's making it very difficult to extract the planet spectrum from the stellar spectrum. So there's a different NASA Pioneers mission called Pandora that I'm on that's going to launch in a couple of years. The goal will be to observe the planets at multiple wavelengths at the same time and try to disentangle these effects. So there are other targets. We're just kind of running into a little bit of noise issues at the moment. I'm hoping we have the answer soon.
All right, we have a question on your left at the back of the room.
Is part of the problem with finding Earth-sized planets that at the distance they orbit, the probability of them being in the plane of the Earth is small?
Yeah, so that's it. Once you get out to the distance of Earth, the probability of transiting is 0.5%. So you have to look at 200 systems with an Earth-like planet in them to find the one that transits. It's a 200 to 1. So that is part of the problem. That's why Kepler had to look at 200,000 stars to try and get the statistics. It's also true that the longer the orbital period, the fewer transits. We have to wait a whole year to see the next one and then wait a whole year to see the next one. So that also makes it hard. They're small and they're far away. They're really hard to find.
All right, let's take another online question. How do the hot Jupiters keep their atmospheres when their stars don't burp?
Yes, so that's a good question. So Jupiter has 1% the mass of our sun. Jupiter's actually pretty massive. So if you imagine it's got a very deep gravitational well. So even though it has an atmosphere and it's right next to the star, it has enough gravity to hold on to its atmosphere. A rocky planet, which is much lighter, 1,000 times lighter, doesn't have as deep a gravitational well. So the star can more easily blow its atmosphere away. So we think it's much more of a problem for rocky planets close to their stars than hot Jupiters.
All right, question in the back of the room here.
Can you expound on the challenges of finding planetary satellites, especially ones that would be potentially Earth-sized?
Sure, so exomoons. So we've talked a lot about exoplanets, and almost all of the planets in our solar system, bar Venus and Mercury, have moons, right? All of the other planets have moons. So if you extrapolate these thousands and thousands of planets we found, some of them should have moons. And there's been very, very dedicated searches for these, especially with Kepler, but with other techniques as well. So with Kepler, we have 2 candidate moons. So what we have are 2 Jupiter-sized planets that have little wiggles at the start or end of their transit. If they're truly moons, they're Neptune-sized moons orbiting a Jupiter-sized planet. So it could be more correctly called a binary planet system than a planet with a moon. They're both candidates. We've tried to confirm them with Hubble, but we still haven't been able to do it. The difficulty of finding exoplanets is multiplied by 1,000 when you're trying to find exomoons. They're so tiny and they're so dwarfed by the signal of the planet. So Roman, this Nancy Grace Roman Space Telescope that'll launch in 2 years, we're hoping to find moons with that, because that'll be much more sensitive.
All right, we have a question up front here on your left.
Thanks for a great talk. You showed us exciting stuff about planets around white dwarfs, and then towards the end you showed us 4.5 billion years of Earth's atmosphere. Can you tell us a little bit about the distribution of system ages and where we think we might fit in the life of a star with planets around it?
Yeah, so that's super interesting, partly because I just had a paper accepted on ages. I didn't plant that question. What we see today is a snapshot of planetary systems at a point in time, right? Like, we don't even know what happened in our solar system before now. There's this idea that Jupiter and Saturn switched places at some point, right? And that was a dynamical thing that happened. So what we do is we have to take this gallery of snapshots of planets around stars of different ages and try to see if we can make a movie, right? We want to know, do planetary systems start like this and then evolve in this way to become this? Or are they very different? Did this system start out differently? The reason this is really interesting is because different theories about how planets form and evolve and migrate usually happen on different timescales. Like, one theory will predict this happens really fast, and one theory will predict this takes 1 billion years. So if you can get these snapshots in time and build this movie of planet formation, you can say, well, it can't be this theory because it hasn't happened yet. It must be this theory. So it's a really good discriminator of planet formation theories, which is what my new paper is. It's coming out next month. Very excited. So yes, it's really important that we look at planets as a function of age. In terms of the Earth, the Earth is 5 billion years old in a solar system that's 5 billion years old, in a galaxy that's 13 billion years old. So there were 8 billion years before our solar system, our sun was born and our planetary system was born, for other stuff to happen. And so this partly comes back to the Fermi paradox, which is the Fermi paradox, Enrico Fermi being like, well, where is everyone, right? Because there were 8 billion years before we were even born for anything to arise and colonize the galaxy. And we don't see it. So where we are, 5 billion years, it's a really interesting number. If you know the Drake equation, so Frank Drake wrote down all of the factors that you would need to know to calculate how common intelligent life is in the galaxy. One of them, the last part of the equation, is the letter L, which is the lifetime of the civilization, right? You could have 100,000 civilizations, but if everyone nukes themselves in 100 years, then that L is low, and there's not a lot of intelligent civilizations left in the galaxy. So far, we've had radio for 100 years. We've almost nuked ourselves several times. So we don't know L. We don't know what the lifetime of intelligent civilizations is. We just have us. So 5 billion years is really interesting, because we're here, and we're doing radio things, and what's next?
Dr. Christiansen, what's the journal your article's going to be published in?
It's the Astronomical Journal, which is out of the American Astronomical Society.
Visit Linda Hall Library to read that journal article next month, right? All right, do you have a question? Yep.
I just wanted to say that I know that when you're talking about NASA's focuses, for the future, you said there's a high emphasis on basically your field, but then obviously NASA as an organization has different priorities, and I know there's another large, part of NASA's focus is looking at planets such as in our solar system, or rather moons in our solar systems that are tidally locked, and they have the potential. I know when they looked at was it Io when they first found that it was volcanic. Right. And I know there's talk about going to, I could be wrong here, was it Europa?
Yeah, Europa Clipper is a NASA mission that's being built and launching soon.
And even further ahead, talk about a submarine to go and look at these methane lakes there. Mm-hmm. Now, obviously, that's a different field to yourselves, but I guess this comes down to my question is the definition of Earth 2.0, because I would presume, say, hypothetically, they do have some success in Europa and they find, bacterial life, obviously very simple life. Just that equation would then open up your field to, I would imagine, times 1 billion in regards to what planets you could find. Are there any, so I guess what I'm trying to say is, are there any way you see in the future that you might look at tidally locked planets, distant tidally locked planets, who might have one side facing the sun, but there might be like a temperate zone in between? Are there any kind of plans to look at those types of, for life?
Sure. Okay, there are a lot of parts to that. So I'll start by saying that NASA has 5 different science divisions. One of them is astronomy, which is the one that prioritized Habitable Worlds Observatory. Another one is the planetary science division, which is specifically our solar system. They have their own decadal survey, which came out last year, and now I can't remember, but they had a top priority as well, which was some mission to some solar system body. So there is also funding and priorities there. They're parallel and separate from the astrophysics division to the planetary science division. To get money to look for life, we really have to make a good argument why we think life exists where we're looking. We don't have a lot of examples, right? We have Earth, which is why we're searching for Earth 2.0, because we know that's where the only place that life exists. If we find life other places, then yes, we will be able to get funding to develop more different missions to prioritize different planets and different types of atmospheres, and that will be super exciting. I will say, JWST, looking at the rocky planets around M dwarfs, most of them are tidally locked because they're so close. So we are looking at tidally locked planets to see if they have atmospheres and then eventually look for life. So we're not discounting tidal locking, which would be cool.
Right, we got time for a couple more questions. Alan, you have a question here?
There's been a lot of discussion lately, or articles I've read about rogue planets, and I know that there's been some discussion of Romans possibly trying to look at some rogue planets. Can you address that just a little bit? I know it's probably a little bit out of your area of emphasis on Earth 2.0.
No, that's fine.
If you can address that, that'd be great.
It's a lot in my emphasis as the lead scientist of the NASA Exoplanet Archive. So what Alan's asking about are rogue planets or free-floating planets. So all of the planets I've talked about so far have a star that they're gravitationally bound to. But what we have found is a large number of planets or planetary mass objects out there in the galaxy that don't seem to be attached gravitationally to a star. And there's a few different ways we find them. But we think the evidence seems to suggest that they're very numerous. They're perhaps as numerous as planets bound to stars. So remember I just mentioned there's this idea that Jupiter and Saturn switched places in our solar system. There's an idea that we had 5 giant planets in our solar system and that there was a whole dynamical thing that happened and one of them got kicked out. That would now be a rogue planet. And that our solar system could have contributed to the population of rogue planets. So Roman is going to do more than two, but 2 surveys that are relevant here. One of them is a microlensing survey, which is another way of finding planets, which we're sensitive to unbound planets that are very far away from us. So that's one survey. The other survey is it's got this wide field imager, which will do an infrared survey of the sky. Now these free-floating planets, they still have some temperature. They're still emanating some heat. So what we do is we find them in the infrared. We do an infrared survey of the sky, and you find little blobs of heat. And those are planets that are just floating out there. So we'll be able to find moons, free-floating planets that way as well. So there's a lot of ways that Roman will help. And I think it'll be really interesting, because again, it tells us about planet formation theories. What does it mean that there are as many planets that aren't attached to a star as attached to a star? What does that mean for how they form or how these planetary systems evolve? How do you kick out? Like we have 8 planets. Did we kick out 8 planets? I don't think so, but where did they all come from? So it's a really interesting open question. And I will say, just a little bit of politics, we don't have rogue planets at the Exoplanet Archive, in part because we can come back to Pluto. Pluto got kicked out of being a planet in 2006, and in part because the International Astronomical Union came up with a definition of a planet. Finally, we're like, we have to decide what a planet is. And one of the 3 things in that definition of a planet is orbiting a star. So that's why before when I said planets, I was like, planetary mass objects? They're small, but by definition not a planet because they're not orbiting a star. So that's the politics. They're not in the exoplanet archive, but we actually secretly are keeping an internal list in case anyone ever changes their mind and decides they should be in. We can be like, here's one we prepared earlier. Here's the list. So I'm just waiting for the pressure of the astronomical community to be like, you should have these planets in. So far it hasn't happened, and I'm grateful, because all of our architecture is set up to support planets around stars. Breaks a lot of things if they don't have stars.
All right, we have a question about midway back in the room.
Your comment about the hope that China will share with us information that they're getting from their 2.0 exploration. And we know that science has historically benefited from cross-border collaborations. Some of the projects that you've been working on with NASA have cross-border collaborations, but not all cross borders. Hubble and the James Webb publish a lot of information, but is that information in native form so that all nations and all scientists will have the same access that NASA has to it and the nations that finance those ventures? And if not, is there anything afoot to cause the collaboration between nations such as China and Russia?
So NASA has a very strong policy that the data that come down from the spacecraft belong to the public. It's taxpayer funded, it's your money, it's your data. And so that's partly why I work at an archive, for instance. Our job is to serve this data to the public and to other scientists. You could recreate the Kepler results from the current archives. You wouldn't need any more information that is not available to redo Kepler science with what's in the archives. Other countries just don't have the same policies. Like even the European Space Agency doesn't have the same policies of the raw and calibrated low-level data products are available for everyone. And there are federal rules in place about collaborating with countries like China and Russia. So I'm not allowed to have what we call bilateral communication with Chinese colleagues. I can't send an email to a Chinese colleague from my NASA email address and ask them a question. I need to CC a European. So it's not a bilateral communication. There's 3 of us. It's not bi. So there are really strict rules about what federal employees are allowed to do and allowed to say. And other countries just don't have the same policies of being open, which is why I say I hope. And I think this new generation of scientists is very open source. You know, young people want to share their codes and their data and how they made everything. It's very, very open, and I think the internet has helped a lot with that. So I see that in the new generation of Chinese scientists as well. They want to be open with the data, and then it's just a question of what will the policy be, which they probably won't get to set. It'll be set down from the government, which is what happens here. Ours is set down from the government.
All right, let's do 2 more questions. I've got an online question, and then back here on your right, the back of the room, Dr. Christiansen, we have a question from a future astronomer.
So there's a lot of galaxies out there, and there's a couple different types of galaxies, like elliptical. So is it harder to observe elliptical or like spiral galaxies and the stars and planets in them?
Yeah, so the question is about different types of galaxies. So I'll start by saying everything I talked about tonight is in our galaxy. There are a couple of candidate extragalactic exoplanets, so signals of exoplanets that might have been from other galaxies, but they haven't been confirmed yet. But if you think about the Milky Way galaxy being a fairly standard spiral galaxy, having a fairly standard distribution of stars, the fact that we think there are billions of planets in our galaxy means we think that there are billions of planets in other galaxies too, which is there are trillions of galaxies, and that's amazing. So one of the things that Roman will do, I mentioned the Nancy Grace Roman Space Telescope, it's doing a survey for all of these different types of galaxies all across the sky, because the distribution of galaxies and their sizes, which you're talking about spirals and ellipticals, different sizes and shapes, that distribution tells us about how the universe formed. How was the universe born, and how does that imprint itself on the distribution of galaxies today? So the Roman will do a lot of these things.
I think Q&A is my favorite part of these programs. Let's end with this question from an online viewer. When we find Earth 2.0, what do we do then? What's next?
I retire happily to a seaside town where I own a secondhand bookshop and I just read by the beach. Okay, so Earth 2.0. If Habitable Worlds Observatory finds a blob that looks like a rocky planet in the habitable zone of sun-like star, the first thing we're going to do is get those spectra. And we're going to turn every telescope that we have towards this planet and spend the next few decades working out what's in its atmosphere. Is it consistent with life? If it's life, what kind of life is it consistent with? People will immediately start sending radio messages in that direction. We already do it. We'll probably make another one of Carl Sagan's cool bookmarks with the humans and the scale model of the solar system and send those. We don't have Arecibo anymore, so we'll have to use something else. We'll immediately start trying to message it. The problem is it will be tens of light years away. So the round time for a message, even if they got it immediately and sent back, is many decades to hundreds of years. And then after that, it's speculation, right? Then it's just like, okay, now what? So characterizing and then working out what's next.
Thank you, Dr. Christiansen.
Thank you.
That was wonderful. Thank you for attending tonight's program. Be sure to sign up for our next public event, November 2nd, on the role of early modern images. Thank you and have a great evening.